in covering lesson 10.3. I split this from 10.2, even though this would have been one single lesson taught in a class, just because 10.3 is very proof heavy and you may want to have that not as part of a really long video. So warning you ahead of time, there's a couple theorems here that we're going to be applying, right? And these are more segment based, so applying properties of chords, and that's going to be using both relationships of arcs and chords and circles to prove. So starting off, if these arcs are congruent, therefore the chords are going to be congruent, or vice versa, because it is an if and only if. If A, B, and CD are congruent and they're both chords in a circle, then the arcs must be congruent. And now this theorem is going to take a little bit of proving, right? And so what we're going to use when we prove these theorems is, again, whenever we're in a circle, when we have radii, all radii are congruent. So that's usually a quick jump to get some congruent pieces here. We'll change the color so I'm not black here. But for example, PD, PC, PB, PA, going backwards a little bit there, are all congruent because they're all radii. P is the center. They've got that point nice and kind of bolded out. We already almost have side, 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 right? Kind of looks like we might have side, angle, side, but notice, right, if I like try to continue this line straight, clearly it's not straight enough. It's not vertical. So what else do we have, right? Given they're congruent chords. It's actually given that these segments are congruent. So we do have side, 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 and it didn't take a lot of steps to get there. However, it's a little bit of steps to use. We don't just have a CPCTC, right, corresponding parts of congruent triangles for these circles, these arcs, pardon me. So let's kind of look at it and see how it goes. So first up, all radii are congruent, a little bit all over with that, but PC congruent to PD, congruent to PA, congruent to PB, all are congruent. Great. Next up, we'll have triangles are already congruent because, right, side, 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 we've got three sides congruent. You do want to be careful with the order, but there's a little bit of flexibility. So PCD is congruent to PAB is how I did it. Could have also said PBA, so order's not as picky. And then we want these angles congruent, right? Because once we say those angles on the inside here are congruent, then we can say, well, central angle's congruent, therefore arcs are congruent. So that's kind of how, sorry, that second arrow is bad, but that's how that proof is going to go. And so this is the reason that we're going to use quite a bit, and it goes vice versa from the last lesson. Even though we used it with math, central congruent central angles have congruent arcs, and we could also say, if we're wanting congruent central angles, we could say congruent arcs have congruent central angles. So be aware, we probably will use that one or two more times just in this lesson alone. Next, AB and CD are chords, and AB arc, that's the arc mark, sorry, congruent for CD arc. So what they're giving us here is, again, similar to last time, label those radii congruent, and they're telling us these arcs are congruent. I should probably use more than one congruent mark, but that's the general idea. So what we're going to do is almost the exact opposite of the last proof. We're going to say these arcs make tell us that the central angles are going to be equal and hence congruent. And then from there, we've got side angle side, side angle side, and these AB and CD chords are going to be congruent from that. So let's see how it gets pieced together. And again, why I'm saying this before I'm revealing the proof is it's always great to, like, hey, we've got triangles, 90-something% of the time we're proving them congruent. So how can we prove them congruent, right? So that's kind of what you're asking yourself. So I'll relabel that chord here. But so clearly we're going to do all radii are congruent. And again, in the same circle, I may have written that in one of my steps, but just make sure you're not jumping from circle to circle, assuming just because things are radiuses, they are congruent or radii. Next, here's that step again. Congruent arcs have congruent central angles. It's a little bit flipped, right? Because now we're going from this CD, arc CD means angle DPC or CPD, if it looks like Cupid, I guess, congruent to angle APB. So that's how I have it. CPD congruent to APB, and therefore we'll just list those as a triangle. CPD congruent to APB because now we have side angle side, and therefore DC congruent to AB by CBC TC. Okay, so that's a nice short proof. Again, typically I like short proofs. I shouldn't need to hint that too much at you. But make sure you know how to do something short and simple like that. And the last one was also, I believe, only 5 steps, right? So nice to get some 5-step proofs after that 8-step one we covered the other lesson. Next, we've got a couple more coming up here. Theorem 10.4 and 10.5. So again, even though these ones do not have names, we may use them. It's more likely they're going to be used mathematically unless the proofs are pretty short. So these are going to say the same thing. They're kind of like converses of each other, but not quite. If QS is a perpendicular bisector of the line TR, then QS must be the diameter of a circle. And the second one is if the diameter of a circle is perpendicular to the chord, in this case chord FD, then it bisects the chord. Right? If we're perpendicular bisect, if we weren't perpendicular, then it might not necessarily be congruent, right? And so I believe we'll be proving the bottom one here. Bottom one, given we've got EG perpendicular to DF, that right angles there, have 8 steps. And again, 8 steps is typically because perpendicular adds a couple, and look what we're proving, right? If we have EG as a diameter of circle, we're going to have that it's congruent because we're basically proving the bisector, right? We've got perpendicular, prove it's a bisector, and prove that those arcs are congruent, right? I kind of missed mentioning that, but it also said for congruent, we bisect the segment and the arcs, FG and GD are congruent, or GD, GF. So good catch there by the proof. So again, I see a picture where we could have triangles, and these lines I'm drawing in as not straight as they are radii. I'm going to use my straight line cheaters. All right, so that's when you start from the right point. But so those lines are supposed to be congruent if I started from the correct point. And then what else? I've got the small triangles here that we're proving congruent. I bet we've got right angles, so that's 2 steps. Perpendicular gave us right angles, and then do we need right triangles or congruent, right? Right now I've got angle side. We also have reflexive. This right here, LC congruent to LC. So we got reflexive and all radii congruent are going to be our first 2 steps. Looks like I put reflexive a little further back, but just continuing to talk through the plan, right? And sorry, I should probably leave these available for you to a little more to copy. But feel free to pause the lesson if you notice I'm going a little too fast. The next slide. So we've got LC is reflexive. We've got LD and LF are radii. So all radiuses are congruent. And now we've got side, side, but now it says angle side, side. Spells a bad word. So that's your hint that it's hypotenuse leg, right? We've got hypotenuse, we've got leg. And so we're going to need right triangles. So again, when it's hypotenuse leg, that typically adds a couple steps. So let's walk through. First, given, straightforward, right? Hopefully you've had time to write that down. If not, again, pause the video to write down the proof. LD congruent to LF is all radii congruent. LCD, and now I went into talking about the right triangles. So these LCD and LCF are right angles because perpendicular, right? Definition of perpendicular means all 4 of those angles are right, and therefore that triangle is going to be a right triangle. Right? So that's the second step. LCD and LCF triangles are right triangles. By definition of right triangles, RT for right. And then LC congruent to LC, there's our reflexive. Right, this piece equals itself, even though it's small, it is needed. And then we have the triangles are congruent by hypotenuse legs, LCD and LCF. And then after that, this is kind of where it gets a little bit weird. The CPCT, we're grabbing, this is part of what we needed to prove, CD and CF congruent. The next part is we need the angles on the inside, the central angles, right? These 2 angles right here. Let me mark with a different color here so it stands out a little bit. These angles here, oops, that was rough, are congruent and therefore the arcs will be congruent, right? Right, so that's what we're looking at there. So we'll erase kind of the extras, yep, we needed angles congruent to have arcs congruent. So got the angles, and therefore DG congruent to GF. And then notice this is very rare, but this is part of the prove, and this is part of the prove. If you have to go an extra step to finish, that's okay. Congruent central angles have congruent arcs. Now, wrapping up the lesson, we've got one more short mathematical theorem. In the same circle or in congruent circle, the two chords are congruent if and only if they are equidistant from the center. So if we're perpendicular and this distance is equal from the center, then AB and CD are congruent. Or, right, if and only if they are, the chords are congruent, right, then this has to be equidistant. So it goes both ways, meaning perpendicular and congruent on the inside. We could prove those, but we will not. It might be in the homework. Feel free to ask that as a question. We can kind of have it filled in to go over. So this is an example. Solving 16 equals 16, therefore 2x needs to equal 5x minus 9. They already gave us the perpendicular. And so 2x equals 5x minus 9, minus 5x from each side to get minus 3x is minus 9. Divide by negative 3, x is 3. And then look, CU. Didn't say find x. We did find x, but now we got to plug it in. You could plug it into either one as a double check, but 2 times 3 is 6, and there's our final answer. And that wraps up this lesson for today. Feel free to shoot me an email or, again, post on the classroom if you got any questions, comments, or concerns.